Okay, here was our first lemma, that if f was holomorphic on an annulus and we did these integrals around circles, that it's constant as a function of which circle you integrate over. So let's try to prove it. So we take two values of t, t1 less than t2, inside the interval little r to big R, and we look at two different values of g, or potentially different values. And you can just subtract the two integrals and get f of t2 e to the I theta minus f of t1 e to the I theta. And there's a difference of two values of a function, so you can use the fundamental theorem of calculus to view this as an integral. So if I take the derivative of this as a function of t and integrate it from t1 to t2, I'll get this difference. So that's what I've done here. The derivative with respect to t of f of t e to the I theta. And again, you could just view f as a function with a real and imaginary part, and you're taking this derivative with respect to t, and then if you integrate that with respect to t, you're going to get a difference of values, just as in the fundamental theorem of calculus. Just looking at the real and imaginary parts separately, there's no big deal here, except that we can evaluate these derivatives in two different ways. So the derivative with respect to t will be e to the I theta f prime of t e to the I theta, but the derivative of the same thing with respect to theta is very closely related. So if I take, so here in this next step, I applied Fubini's theorem to interchange the order of the integrals, which I can do because I'm assuming f is holomorphic, so the complex derivative is continuous, so there's no issue of interchanging the order of integrals. But now I view this derivative as something closely related to the derivative with respect to theta. So if I take the derivative of ft e to the I theta with respect to theta, using our general chain rule, we get f prime t e to the I theta, and then we'll have ti e to the I theta by taking the derivative of the inside. And so I've canceled part of that with it here to get me back what I have there. But now what are we doing on the inside integral? We're integrating a derivative with respect to theta from 0 to 2 pi. And so you'll get the difference of values at 0 and 2 pi, but since e to the I theta is 2 pi periodic, you get the same value at 0 and 2 pi. So this inside part is always 0. And therefore, we get that g of t2 is always equal to g of t1. Okay, so that proves the lemma, and notice the crucial thing here is that using the generalized chain rule and the Cauchy-Riemann equations are sort of lurking in the background as to why this works. Let's prove the next lemma, which is a special case of the Cauchy integral formula on a circle. So, to compute this, we have to use the lemma we just proved. So we take a little r greater than the modulus of z, so z is in the unit disk up here, and we'll evaluate this complex line integral on this disk. And so if you follow the definition, we put in, up here you would get r I e to the I theta, but we canceled some i's since there was an I over here that disappeared right there. And so the expression we have is right here. And we can view this as integrating a holomorphic function with respect to theta. So it's like this, where little f I've written here is w over w minus z. And this is certainly holomorphic if w is not equal to z, so if the modulus of w is greater than the modulus of z. Okay, and by the previous lemma, this will be constant with respect to the circle R that we're integrating over. So this expression here does not depend on R, so basically what we can do is send R to infinity, and the z in the bottom is not going to matter when you take the limit. I'm not going to go through the details of computing the limit, but basically when you send R to infinity, you can show that the z will disappear, and you basically end up with this expression. And so this will give you 2 pi, then we also divide by a 2 pi, and so we get 1 in the limit. Finally, let's prove the third lemma, which was continuity of the difference quotient function on the product set. So again, here it was. We have a holomorphic function, and we define big F to be the difference quotient when z is not w, but it's the derivative otherwise. And we just want to show that this is continuous, because in our proof of the Cauchy integral formula, we had to integrate in one of the variables and know that it was sort of continuous in a parameter. Okay, so if we take a point z0, w0 in the product set with z0 not equal to w0, continuity will follow from the continuity of f, because there's no issue. We just have the difference of two continuous functions divided by a continuous function. So when the bottom's not going to 0, there's no issue about continuity. The real issue is on the diagonal, a point z0, z0 in the product set. To prove continuity on the diagonal, let's look at 2 points z and w not equal that are close to the point z0, z0. And we're going to evaluate the difference quotient using an integral. So here's sort of a trick. I'm going to look at f along the line segment connecting z and w, and if z and w are close to z0, then every point on this line segment will be close to z0. So if I take the derivative of this with respect to t, again with the generalized chain rule, I'll get the complex derivative of f on the line segment times z minus w. That's just going in here and taking the derivative of tz to get z, and the derivative of 1 minus t times w to get minus w. Okay, and so we're going to use the fundamental theorem of calculus, that this difference, which you'd obtain by plugging in 0 for t, will give me f of w, and plugging in 1 for t will give me f of z. So I can integrate this derivative from 0 to 1 to give me the difference f of z minus f of w. But then I can divide by the z minus w to get that the difference quotient is actually equal to this integral on a line segment of the derivative of f. And now this makes it real easy to compare the difference quotient to the derivative. So if I have the difference quotient minus the derivative at z0, I just put everything inside the integral and put absolute values through. And then we're assuming that f is holomorphic, which we said we built in that the complex derivative will be continuous in this case. And so if we can make this quantity here small just by making z and w close to z0. So that means that we can prove the continuity at z0, z0, at least using points that are off the diagonal, but for points on the diagonal, the desired estimate we need follows also from the continuity of f prime. So I won't do all the epsilons and deltas, but this is the basic idea. So this establishes the three lemmas that we needed to prove the Cauchy integral formula on a circle. So now let's look at some of the really important applications.